Hello everyone, welcome to our presentation. Today we'll discuss the overview of Wi-Fi 6 technology development. This is for the course of EE 5135. I'm Zhou Tongtong and my partner.
龙逸晨
Our presentation is organized into these 6 parts, including introduction, system architecture, physical layer design with the transmission technology and the coding technology. Then we'll introduce the performance evaluation and make a comparison of Wi-Fi 5 and 6. Finally, we'll conclude and introduce the future trends.
Now let's move on to the introduction part. For this part, let's first explore the evolution of wireless communication technologies. From this timeline chart, we can clearly observe the iterative upgrades of Wi-Fi standards. We can see that Wi-Fi 4 is released in 2009 with a max speed of 600 megabits per second, and Wi-Fi 5 is released in 2012, which the speed is increased to 3.6 gigabits per second. And our Wi-Fi 6 is actually released in 2019. The speed is achieved to 10 gigabits per second, optimized for high-density IoT deployment. Next, let's derive from let's dive into the driving force and motivation behind this technology advancement. For this part, let's explore why Wi-Fi 6 becomes essential. The newly emerging applications have dramatically increased demands for data transmission capabilities, including high-definition video streams, cloud computing and IoT, virtual and augmented reality. Such technical needs have driven the introduction of new WLAN standards. While addressing modern communication needs, previous Wi-Fi standards faced limitations such as poor spectral efficiency, limited network capacity, and also high latency. To resolve these challenges, Wi-Fi 6 introduced some groundbreaking technologies which enhance overall network performances. Now let's dive into the system architecture of Wi-Fi 6 to understand how this technology works together.
Now let's move to the part 2, system architecture. In this section, we'll detail the system architecture of Wi-Fi 6, including its core components and the data flow mechanisms. Let's focus on the 3 core components of Wi-Fi 6 system, including access points, which is denoted by AP, client devices, and the backhaul network. Firstly, the access point, which denoted by AP, acts as a central hub, managing communication with all client devices. Wi-Fi 6 APs are equipped with 8 multiple by 8 MU MIMO antenna array, enhancing signal direction and user capacity through the dynamic beamforming. They also integrate an OFDM-A schedule and LDPC encoding currents to optimize resource allocation and error correction. Additionally, AP manages client device wake-sleep cycles to reduce power consumption. And the second, client devices denoted by STA. STAs include smartphones, laptops, smart home devices, etc. These devices incorporate low-power RF modules and support target wait time. They also feature 1024 QAM optimized receivers with high sensitivity, ensure reliable data transmission, even at low signal-to-noise ratios. The design extends battery life and makes connectivity stable. Last is the backcore network. It connects multi-APs and aggregates data to the core network. In Wi-Fi 6, it supports 10 gigabits per second interfaces and 60 GHz millimeter wave links. This boosts overall network performance and stability. This is a figure shows that physical architecture of Wi-Fi 6 mainly focuses on AP and STA communication mechanisms. We can see the network here. Next is the Wi-Fi architecture data flow mechanism. Let's analyze its downlink and uplink mechanism. Firstly, in the downlink transmission, the AP uses OFDMA to allocate resources units to different STAs. Data is transmitted simultaneously across multi-subcarriers. This allows multiple users to receive the data without resources conflicts. Combined with MU-MIMO beamforming, signals are precisely directed to the target STA, enablling the parallel transmission and dramatically improving the spectrum efficiency. For the uplink data flow, the AP first sends a trigger frame to synchronize the STA transmission, and the STA uses a side IOs to transmit data dynamically to minimize the collisions, which ensures the scalability, high efficiency, and data uploads across devices in the same channel. All above these optimized mechanisms are why Wi-Fi 6 excels in high-density multi-user environment, makes its high-speed stability, and makes the scalability better.
Now let's move on to part 3, physical layer design and transmission technologies. In Wi-Fi 6 physical layer design, we focus on three groundbreaking technologies that redefine wireless performance. 1. OFDMA, 2. MU-MIMO, 3. 1024 QAM. Okay, now let's move on to OFDMA. Let's see how it differs from traditional OFDM. In principle, OFDMA means orthogonal frequency division multiple access. It's an enhanced version of OFDM and a core innovation in Wi-Fi 6. As covered in class, OFDM divides a channel into orthogonal subcarriers but allocates the entire bandwidth to a single user at a time, which is TDMA, time division multiple access, leading to inefficiency in dense environments. OFDMA, however, splits the channel into smaller resource units, enabling FDMA. This allows multiple users to transmit or receive data simultaneously on the same channel. It also makes it far more efficient in high-density scenarios, such as smart homes, industrial automation, and public hotspots. And for the performance optimization, compared to OFDM, OFDMA achieves approximately 30% higher spectral efficiency and also about 40% lower latency in high-density settings. It excels in scenarios where simultaneously connectivity is critical. For example, when multiple devices, phones, smart speakers, sensors, connect to one AP. OFDMA dynamically allows RUs to meet each device needs without contention. Next, let's explore the second technology, MU-MIMO. This one takes multiple user communication to the next level. The principle of this one is that this one extends traditional MIMO by enabling simultaneous uplink and downlink streams for multiple users. The full name of this one is multi-user, multiple input, multiple output. Using precise beamforming, it directs focused signal beams to target users, minimizing interference and maximizing signal strength. For the performance optimization, compared to the single user MIMO, MU-MIMO boosts throughput by about 50%, especially in crowded environments like stadiums or office buildings. It supports up to 8x8 MIMO configurations, dynamically increasing spatial streams and data capacity. Okay, now let's turn to the third pillar of Wi-Fi 6 physical layer, 1024 QAM. This one is a key enabler of Wi-Fi 6 raw speed. For principle, 1024 QAM is fully named as quadruple amplitude modulation. This one increases the data carried per symbol from 8 bits to 10 bits. For the 8 bits, it's of the 256 QAM. This one packing more information into each transmission. While this boosts data rates, it demands a higher SNR, which is signal-to-noise ratio, for reliable decoding, require clear channel conditions, and the performance optimization during strong signal conditions. 1024 QAM achieves about 25% higher throughput compared to the 256 QAM one. This makes it ideal for bandwidth-hungry applications like 4K or 8K video streaming, large file transfers, and real-time cloud computing. With this one, we've covered Wi-Fi 6 core physical layer transmission technologies. Next, we'll dive into its coding technology, LDPC, to understand how errors are minimized in high-speed data streams.
Now let's move on to the part 4, physical layer design, mainly focus on the coding technology. Let's see the diagram of the physical layer data flow design, which can be broken into the 6 parts. First, data inputs. Raw data enters the system through the input module. Then the encoder processes the data. Data is transmitted over the wireless channel, and then at the receiver, the decoder reconstructs the original data by correcting errors introduced during the transmission. The restored data is then divided through the output module. The structured data flow provides the framework of the advanced error correcting. We now provide a detailed instruction to low-density parity check, which is LDPC coding. It is based on a sparse parity check matrix, which is characterized by its large dimension and high sparsity. It supports various coding rates, such as listed here, 1 divided by 2, 2 divided by 3, etc., to meet different application scenarios and transmission requirements. The coding processes involving preparing a message vector, deriving a generator matrix, and generating the encoded code words. Then, in the decoding process, the belief propagation algorithm is used. By exchanging probability information in a vector graph, this iterative decoding method significantly improves the accuracy of error correction, reduces packet loss, and increases the data throughput in high interference environments. Finally, compiled to the conclusion course, LDPC coding performs close to the channel limit. Despite its more complex encoding and decoding, it shows significant improvements in error correction and reliability. In this slide, we show the simplified encoding and decoding process as we discussed in the class. First, we should generate a message, which is equaled by the m multiplied by g. G is the generated matrix. Then calculate the LLR, which is initial log likelihood ratio from the received signal. Then update the LV2C, which is the message from the variable node to the check node, and the message from the check node to the variable nodes. Finally, with the calculation above, we can update the value of the L final. Then we can decide the code words whether it's equal to 0 or equal to 1 by these conditions. The encoding process terminates when this equation C bar multiplied by transposition of the H matrix is equal to 0, or the maximum number that is set of the iterations it is reached, generally 8 to 12. When the process does not converge within a specific iteration limited.
Alright, now let's dive into Chapter 5, Performance Evaluation and Comparison. Here we are going to break down how Wi-Fi 5 and Wi-Fi 6 stack up against each other across some key metrics. By looking at these comparisons, we can really see where Wi-Fi 6 makes its improvement and what technologies are making that possible. And now let's break down each performance matrix and look how Wi-Fi 6 improved them. The first one is spectrum efficiency. This one measures how much data can be transmitted per unit of bandwidth. Wi-Fi 6 boosts this one by about 30% using OFDMA, which helps optimize resource allocation, especially in the crowded environment. And the second one is throughput. Throughput refers to network speed and capacity. With support for 8x8 MU MIMO, Wi-Fi 6 boosts throughput by 50% compared to Wi-Fi 5. Especially in crowded places. And the third one is energy efficiency. This is about finding the right balance between power consumption and data capacity. Thanks to TWT, also named Target Wake Time, Wi-Fi 6 achieved around 70% better energy efficiency. This one is super important for battery-powered IoT devices. And the fourth one is latency. Latency affects real-time responsiveness. By using OFDMA and smarter scheduling, Wi-Fi 6 reduces latency by about 40% in high-density scenarios. And the last but not least one, the bit error rate. This measures transmission reliability. With LDPC encoding, Wi-Fi 6 significantly cut down BER under high signal-to-noise ratio conditions, ensuring more stable communication. All these metrics together show why Wi-Fi 6 is a big step forward. Now let's see how these improvements stack up in a direct comparison. Here we have two tables. We can see from the table that this table contrasts Wi-Fi 5 and Wi-Fi 6 across technical features and performance metrics. Let's first see the technical features comparison. We can see from the table that Wi-Fi 5 is released in 2013, while the Wi-Fi 6 is in 2019. And the Wi-Fi 5 is only in 5 GHz, while the Wi-Fi 6 have 2.4 GHz, 5 GHz, and also 6 GHz. And also there are some techniques that only Wi-Fi 6 have, such as OFDMA and TWT. And the second table, we can see the performance matrix comparison, which we have already discussed before, just now, sorry. These numbers underscore Wi-Fi 6 transformative leap in speed, efficiency, and reliability. Next, we'll summarize our findings and look ahead.
Finally, move to the part 6. We'll give a summary and discuss the future trends. Wi-Fi 6 core strengths can be split into these two parts. Exploring significant improvements with enhanced network capacity, reduced latency, and better energy efficiency. 6 to the technologies, as we discussed above, like OFDMA, MU-MIMO, 1024 QAM, and TWT, etc. Wi-Fi 6 optimized performance and exists in high-density environments like offices, stadiums, and homes. Wi-Fi 6 journey continues with Wi-Fi 6E and advanced optimizations. Wi-Fi 6E introduces 6 GHz band, unlocking massive bandwidth to reducing the congestion and boost performance. Future research directions include smart spectrum management, dynamic beamforming, and more advanced interference mitigation techniques. This optimization will further boost Wi-Fi 6 performance across different scenarios. Through this presentation, we have explored Wi-Fi 6 core innovations, physical layer design, performances, and the future potential. That's all. Thank you.